You know, inside your computer, there's a tiny, tireless little brain, the microprocessor. And it's an absolute beast at math, executing billions of instructions every single second. But here's the thing, an instruction is just a command, like add or move. To actually do anything useful, it needs numbers. It needs data.
So that's the real question, isn't it? How on earth does a CPU, moving at these unbelievable speeds, find the exact piece of information it needs right when it needs it? This isn't just a simple search. It's a high-stakes, high-speed data hunt, and it's happening trillions of times a second. It is the absolute foundation of everything your computer does. Okay, so let's really get into this. I want you to picture the CPU as a master chef working in a giant professional kitchen, and the program it's running, that's its recipe book. But, you know, a recipe that just says mix is, well, it's totally useless. Mix what? Where are the ingredients? The recipe has to be specific about where to find everything. Right. An instruction like add is really just a verb. It tells the chef, our CPU, what to do, but not what to do it to. That what, the ingredient, is called the operand. So the CPU is constantly asking, okay, add, what? Move, this, to where? It needs to find its ingredients to get any work done. And this is exactly where addressing modes come into play. It sounds technical, but an addressing mode is simply the method the instruction uses to tell the CPU where to find its data. It's the where part of the recipe. It's what turns add into add the sugar from the bowl on the counter. So naturally, what are the fastest ways for a chef to get ingredients? Well, it's when they're already right there on that little prep counter in front of them. For a CPU, that prep counter is its set of internal registers, a small amount of super fast on-chip storage. The simplest and fastest method is what's called implied addressing. Here, the instruction itself implies what data to use. An instruction like CMA or complement accumulator doesn't need to specify a location. The CPU just knows this operation always applies to the data sitting in one specific register, the accumulator. It's like the recipe just says, flip the egg. The chef already knows it's the egg in the pan right in front of them. No searching required. Okay, next up is register addressing. This is like the recipe saying, pour the salt from shaker C into bowl A. Both the salt shaker and the bowl are right there on the prep counter. An instruction like MOV-AC tells the CPU to copy the data from one register, C, and put it directly into another, A. It's incredibly fast because the data never leaves that immediate workspace. Then there's this really clever one called immediate addressing. In this case, the data isn't fetched from somewhere else, it's literally baked into the instruction itself. MVIB02H means move the value 02 hex immediately into register B. The ingredient, the value to, is right there in the command. Now check this out because this image shows you exactly how it works in memory. The instructions command, the operation code or opcode, is stored at one address, and the data, the operand, is sitting right there in the very next memory slot. The CPU fetches the command, and bam, the ingredient is immediately available, right behind it. Super efficient. But of course, what happens when the ingredients aren't on the prep counter? Well, our chef has to walk over to the pantry, what we call main memory, or RAM. This is a much bigger storage space, but every single trip to the pantry takes more time. Direct addressing is the most straightforward way to find things in the pantry. The instruction gives the CPU a specific fixed shelf number, which is just a memory address. So JMP2085H tells the CPU to go directly to memory location 2085 hex to find what it needs next. It's simple, but it's also pretty rigid. Now, register indirect addressing adds a really powerful layer of flexibility. With this one, the instruction doesn't contain the address itself. No, instead it points to a register that holds the address. Think of it like the recipe saying, check the sticky note on the counter. It tells you which pantry shelf to go to. This is a game changer because the program can change what's written on that sticky note, which allows it to access different data using the very same instruction. So this is the really crucial difference right here. Direct addressing is like having a specific street address hard-coded into your GPS. It only goes to one place. Indirect addressing is like having the phone number of a friend who knows where the party is tonight. That second option is way more dynamic and gives programmers a ton more power. And believe me, it gets even more sophisticated. We won't go too deep here, but architects have come up with all sorts of clever combined modes. Imagine a recipe that says, go to the shelf number written on the note, then go 3 shelves up and 2 to the right. By combining a base location with some kind of offset, these modes are absolutely essential for efficiently working with complex data, like a big table of information. Now, all these different methods exist for a very important reason, and that reason comes down to a fundamental trade-off. It's a balance between power, flexibility, and most critically, speed. The way our chef decides to find an ingredient has a direct impact on how fast the meal gets cooked. This right here. This is the key, the single most important takeaway. Every trip our chef takes to the pantry takes time. The more the CPU has to go out to main memory to fetch either instructions or data, the slower the whole program runs. This is the bottleneck. So minimizing these memory accesses is the name of the game in designing a fast processor.
And this table just illustrates that trade-off perfectly. You've got modes like immediate and register, which are lightning fast because they don't require any extra memory trips. The chef stays right at the prep counter. But they're limited. Then you have modes like register indirect, which give you the flexibility to access a huge memory space. But they come at a cost, that extra memory reference, that extra trip to the pantry. Let's make this real with a concrete example. A single, powerful instruction called call can require 5 separate trips to memory. Just think about that. This one command, which basically tells the program to jump to a different part of the recipe, is one of the most time-consuming operations there is. But why so many? Well, as you can see here, it's a multi-step process. The CPU has to make 3 trips just to fetch the full instruction itself, the command, and the 2 parts of the address it needs to jump to. Then, before it can even go, it has to make 2 more trips to save its current location so it knows how to get back later. Each of these 5 steps is another slow walk to the pantry. So you might be wondering, how does the CPU manage all this? How does it read an instruction and instantly know which addressing mode to use and how to orchestrate this incredibly complex data hunt? Well, that's where the real brain of the operation comes in. Meet the instruction decoder. This is the part of our chef's brain that actually reads and understands the recipe. It's a critical piece of hardware that looks at the binary pattern of an instruction, its opcode, and immediately generates the precise sequence of electrical signals needed to carry it out, no matter how complicated it is. And this all happens at a mind-boggling speed. This slide shows the complex dance of signals the decoder sends out in a single clock cycle just to fetch one instruction from memory. And get this, it hasn't even started looking for the data yet. This is just step 1. This microscopic, nanosecond-level choreography is what makes all of modern computing possible. This quote just nails it. It perfectly captures the heart of our entire discussion today. Designing a CPU isn't just about raw speed. It's about making really smart choices. Every single addressing mode is a carefully balanced compromise between flexibility, power, and the ultimate price of performance, the number of trips you have to make to memory. And that really brings us to the final question, a debate that has literally shaped the computer industry for decades. Do you build a processor with a rich, complex set of instructions that can do a lot in one step? That's the CISC approach. Or do you build one with a reduced, simple set of instructions that execute ridiculously fast? The RISC approach. There's no single right answer, and it's a fundamental trade-off that designers are still grappling with to this day.
Thanks for watching. Please visit the channel for such more content, and don't forget to subscribe the channel and like if it is helpful to your knowledge, and comment if something is wrong.